In this video, we explain two applications of the motion of charges in magnetic fields that we just analyzed before. They're going to be the velocity selector and the mass spectrometer. So the first one, the velocity selector, is a device that is going to select charged particles by the velocity, only the velocity. And the key to understand this velocity selector is that only for certain velocity there is going to be a balance between the electric and the magnetic forces exerted on the charged particle. So imagine the following set, where you have an electric field, a uniform electric field that is pointing downwards, as in the drawing. You could produce this, for instance, by a capacitor with the positive plate here, okay, and the negative plate here. So you have this electric field given by these red arrows. On the other hand, you create a magnetic field. We still have not described how you create them, but we will do in the next unit how to create magnetic fields. We would see to it in Unit 15, that is devoted to the sources of the magnetic field. Okay, so anyhow, you manage to build a magnetic field that is also uniform, but in this case is entering the slide. Okay, that is why we represent it with x's. That means that it's a vector that is perpendicular to the screen and entering this screen. Okay, so in this case, if you have a positive charge inside this area here, there are going to be electric and magnetic forces exerted on it. So the first one, the electric force, is going to point towards the same direction as the electric field, because the electric force is equal to the charge times the electric field, and as the charge we've supposed it was positive, then the electric force is going to have the same direction as the electric field. On the other hand, we can also calculate what is going to be the magnetic force. If you remember, this is equal to the charge times the cross product between the velocity and the magnetic field. So to derive this force in this case, we have to use the right hand rule. So you first of all point we know that we are thinking that the particle is moving towards the right. Okay, so then you put your index towards the right, you put your middle finger into the screen, and then your thumb leaves you pointing towards the upper part, okay, towards upwards. This is going to be the magnetic field. So we can find a point in which the magnetic force and the electric force exerted on this charge moving towards the right can balance each other. Okay, we know that the electric field, the electric force in magnitude is going to be equal to Q times E, and in this case, as the velocity is perpendicular to the magnetic field, this cross product brings you that this force, the magnetic force, is going to be Q times V times B. Okay, the speed times the magnetic field. So let's imagine that for a particle there is a balance, okay, between the magnetic field and the magnetic force and the electric force. This is for some particle the electric force is equal to the magnetic force, and as you know, they're each pointing, they have opposite directions. So if they are balanced, this means that the total force in vectorial form is going to be 0. Okay, so when could we have this case? This case would be when Q times E, which is the electric force, is equal to Q times V times B. Okay, here you see that this is going to be independent of the charge, and that this balance is going to be attained only if the speed of this particle is equal to the ratio between the electric field and the magnetic field. Okay, so just for those particles that have this velocity, the magnetic force and the electric force cancel out, and the charge just moves through this region without noticing that there is any electric field or magnetic field, because it will not suffer any net force. Okay. So this is what we have here written. So this is the velocity for which so charges that have this speed, they will be able to cross this area without noticing that there is anything. Okay. However, what if the speed is higher than this value? Okay. What if the speed is higher than E divided by B? In this case, that means that the electrical force is going to be bigger than the magnetic force. And in our example, if there was a positive charge, then the electric force is bigger than the magnetic force, and this is going to be deflected towards the upper part. So the particle is going to end up here. Okay. If the velocity, the speed is weaker than the ratio between the electric field and the magnetic field, then this means that the magnetic force is going to be bigger than the electric force, and this is going to deflect. This is going to be deflected toward the lower part of the region. Okay, so in any case, it's going to, if the velocity, the speed is different from E divided by B, the particle is going to deflect. So only those particles that have exactly this velocity are going to be able to exit this area. Okay, so this can work as a velocity selector, because we can enter with charges at very different speeds, but only those charges that have this speed are going to exit this region. The rest will be deflected either to this plate or to this other plate. The second application I wanted to explain is the mass spectrometer. So this mass spectrometer is a device invented in 1919 by Francis William Aston to measure the mass of isotopes. If you remember, an isotope is an atomic variant of a chemical element in which the number of neutrons is different. Okay, it has the same number of protons, and this means the same charge, but the number of neutrons is different. So the mass of the isotopes are different, but their charge is the same. Okay, so here with this device, we want to know. The objective with this device is try to separate isotopes. Okay, so what we're going to be able to show is what is the ratio between the mass of the isotope and the charge. We're going to be able, measuring several quantities, as I will show you later on, we're going to be able to evaluate what is this ratio. Okay, so the first thing is this mass spectrometer consists of a source that's going to output electrical charges, the isotopes that have to be electrically charged, and to control the speed, what we're going to do is use a potential difference. Okay, so if you know the potential difference, then you can know the change of electrostatic energy, and this change can be converted to kinetic energy. So this is the first idea. This is the potential energy. Okay, this is the electrostatic potential energy being converted into kinetic energy. So from here you can see that the velocity is going to be you're going to be able to change the velocity by changing the potential difference here in the source. Okay, so this is the first idea. The second idea is, once you enter this region with this velocity that you control with the potential difference, the particle enters a region where there is a uniform magnetic field. In this case, the uniform magnetic field is perpendicular to the screen, but pointing out of the screen. Okay, this is why we've put points and not crosses this time, because crosses mean vectors that go into the plane, and dots mean vectors that go out of the plane. Okay, so here we have a magnetic field that has and direction perpendicular to the screen and out of the screen. So once the particle enters the region, it has this speed here, and you have a magnetic field out of the screen. So they're both perpendicular, and you can calculate the force, the magnetic force, as QVB. This is Q, the velocity, times the magnetic field, because they're both perpendicular. And to know the direction, you just have to use your right hand and point towards upwards with the index because of the velocity, and out of the screen with your middle finger, because that is the magnetic field. So your thumb leaves you pointing towards the right. Okay, so this is the direction of the magnetic field. So this is going to provide you with a semicircular path that has a radius given by r. Okay, so here we have again the magnitude of the force. So from here we can derive what is going to be the square of the velocity, because we know that the magnetic force is going to provide a normal force. This is going to be equal to the mass times the normal acceleration, as I was explaining before. This is the normal acceleration, and as you know, the normal acceleration is related to the velocity as the square of the velocity divided by the radius of the circular path. Okay, because here it begins a circular uniform motion. Okay, so this is again the magnetic force. Put as mass times the normal acceleration, and this has to be equal to QVB. Okay, so from here you can derive what the square of the velocity is going to be from the magnetic force. Okay, so here you have two expressions, and what you can do is, as the square of the velocity is equal at both, you can equal this part to this part and try to find out what is the ratio between the mass and the charge. Okay, so from equaling these two, you show that this is 2 times Q difference of potential divided by m has to be equal to square r square q square b divided by m square. So this square goes with this one, and then you can end up having and this q goes with this square q. So m divided by q is going to give you you pass that m and that q there, and then you have square r square b divided by 2 times the potential difference. Okay, so this is what I was telling you at the beginning, that by managing to change the potential difference with which you accelerate the charged particles and you insert them into the area, and by controlling the magnitude of the magnetic field, and by measuring the radius, okay, you can derive what the ratio between the mass and the charge of the isotope is. To measure the radius, what is usually done is just follow the wake of the charges that go through it. And to do so, what you can do is to put some gas here inside this area that has a very low pressure, and then inserting many charged particles with this speed, because you've accelerated with this potential difference. Then those particles, when they are going through their path, they're going to be knocking on the molecules of this low pressure gas, and they're going to excite these molecules, and you're going to be able to see the wake, because those molecules that have been excited are going to come down to a more fundamental state, and they're going to outsource the change of energy of the electrons with the emission of a photon. So they're going to show light on the wake. Okay, so that's how you measure the radio. And with this ends the slides and the theory that I wanted to tell you about Unit 14, and you can manage now to do all the exercises.